In the last video, we looked at relationships between temperature, specifically temperature changes, and heat for a single object. Those single object relationships looked like this. The heat is equal to the heat capacity times the temperature change. The heat is equal to the mass times the specific heat capacity times the temperature change. You'll use one of those two when you have one object. But what happens when you have more than one object? Now each of these applies to a single object. So if you had an equation that related heat flows between two objects, then that would be easy. So suppose you had a hot object, like a block of hot steel or something, and you put it in contact with a cold object, and you wanted to figure out what the final temperature was going to be. Now let's suppose that you knew the mass of the hot object was this, and the specific heat of the hot object was that, and the final temperature of both of the blocks was this, and the initial temperature of the hot object was this. So I'm defining some symbols for things that are in my problem here. The mass of the cold object is here. The specific heat of the cold object is here. The final temperature is the same for both objects. They'll come to the same temperature, but the initial temperatures were different. So here's my problem. Find this. Find TF. Alright, well, I can use the fact that energy is conserved for the first step is to write an energy conservation equation. And if I don't have any work being done, and I usually don't in a chemical system, usually there's no work, I could call this a heat conservation equation and get away with it because there's no work involved with this. So we can use the first law form where the energy change is equal to just the heat. Now, what two objects do I have? I have my block of hot steel and I have my block of cold steel, and they both will have their own Q's associated with them. And all of the Q's have to add up to 0. So you have to identify all your objects. I got a hot object and a cold object. Maybe they're blocks of steel or something. And they have their own specific heats. Now if I say both of these are blocks of steel, they'll both have the same specific heat capacity. And how about I just simplify things a little bit and just write that as S for both of them. Now, this is a master equation. It's the first thing that I do in a problem like this because it's going to relate all the little Q's, which I can then break down using one of the two tools that I already know. So, the second step is to replace the Q's. So I'm going to replace the Q hot with, let me see, I know the mass of the hot, it's M hot, times S times the temperature change, which is the final temperature minus the initial temperature of the hot block, which was T hot. And then I have Q cold, and I can replace that with the mass of the cold block. I'm going to use msΔT again, mass of the cold block, times the specific heat, which is the same as the one over here, times the final temperature minus the initial temperature of the cold block. And all of that has to add up to 0. So now I have a more complicated looking equation. And the third step is solve for the unknown. Alright, what's the unknown? It's the TF. And when I say solve for TF, it means I have to get the TF all by itself on one side of the equation. but it's wrapped in these parentheses here and here. So the first thing I have to do algebraically is get rid of the parentheses by multiplying this out. So we're not doing any more chemistry here. It's pretty much Algebra 2 from high school from this point on. This first term is going to become ms times this minus ms times that. And now I'm going to do the same thing over here. So I've got my TFs out of the parentheses here. I can collect them together. This one's m hot times s and this one's m cold times s. I can factor that out. Now what I'm going to do with these negative terms here that I haven't looked at yet is I'm going to add them to both sides of the equation. And that'll move them over to the other side, away from the TF, which is what I'm trying to do. Get the TF all by itself. So when I add this to both sides on the other side, you're going to get this. And I'm going to add this. So here's what my equation looks like at this point. All I got to do to finish it is divide both sides by this. And I have an equation for the final temperature. Now I'm writing it in kind of a funny way. You may wonder why I'm doing it like this. I could just do divided by the whole side, right? And then that would be simpler. But I'm going to see a pattern here that may help me out in the future. What you're seeing here is, first of all, you're seeing an S over an S. You can S on top and S on bottom will cancel. So it turns out to solve this problem, I did not need to know the specific heat of the blocks if they were both the same material. That was going to cross out. So that's one simplification I get. Another simplification is that I notice this is a weighted average. So it's weighted by mass in this case, because I'm taking the mass of the hot divided by the total mass of both of the objects as a weight for this, and the mass of the cold divided by the total mass of both of the objects as a weight for this. So what I'm getting is a weighted average of the two temperatures as my answer here. Now, if this temperature was, I don't know, 40, and this temperature was 20, if it was a 50, if both of the blocks were the same size exactly, if this one was 40 and this one was 20, I would expect a 30-degree final temperature. It's like halfway between. But if there's more of the hot block than the cold, it will be weighted towards the hot. So you'll see a higher temperature there.